Lesson number 33, the photoelectric effect. This is actually a really important section of the quantum mechanics chapter because we get to really start to apply a lot of what we've already seen with like E equals HF, but a lot of other ideas to explain stuff that can be observable to us. We can actually see the results of quantum mechanics and actually make it somehow useful for us. I'd really suggest that you go through anything related to this section very carefully because, again, there's a lot of new language that we're giving to you, and it can just be kind of hard at first to sort it out when you're trying to do things with all the questions. So that'd be where I'd suggest you be a little bit careful. So we're actually going to start by looking back at Heinrich Hertz's experiment. You'll remember he was the person who was trying to confirm Maxwell's 5 postulates. Now, we're not trying to look at that again. We're not trying to say, hey, what was he doing there? But instead, we're going to talk a little bit specifically about when he was looking at that antenna ring and he was trying to look for the little sparks that were jumping between it. The problem he had was the little sparks just weren't that bright. And that's a problem because he needed to do measurements to make sure that the frequency of the EMR that was being produced from the AC generator he had matched the frequency of those sparks, because that would show frequency of what we're producing or are using to produce the EMR matches the actual EMR that's being produced. So he came up with an idea. He said, how about I put this whole thing inside a dark wooden box and I'll put a little glass window on the front, and then I can kind of cup my hands around it and stare into it, and because it'll be dark inside, it should be easier to see the sparks. Problem was, the sparks were harder to see. They actually got less bright. And he's a little bit confused because, maybe you'd say, well, the low frequency AC radiation, maybe it's being like blocked by the box or something. He was able to show that nope, the wood and stuff wasn't blocking low frequency AC radiation. So he's like tinkering around with ideas and he's like trying to switch stuff out and try different things. And, good job. You got to try some different stuff and see what works. He switched the glass window to quartz. And it did make it maybe a little bit tougher to look through because quartz is kind of milky and everything like that. But now the sparks were bigger and brighter and easier to see. So Hertz is thinking to himself, why is this different? What's happening here? Why is quartz different than glass, or how is it different? And about the only thing that he can really kind of center on is that although glass blocks a lot of UV radiation, at least the glass he was using, quartz doesn't block UV. So he makes a bit of a prediction. It's almost like, an afterthought in everything he's doing here because he's focusing on proving the 5 postulates. But he says, you know what? I bet there's random UV that's shooting around in this room and it's easily able to pass through the quartz. It hits the ring and kind of knocks those electrons loose a little bit. But he doesn't try to explain it. He doesn't try to understand why that's important or anything like that. He just kind of writes it down, but he does because he doesn't know if someday somebody will figure out there's something important about that and maybe come up with great discoveries. Along comes Einstein. This is like a couple of decades later sort of thing. And he says, aha, I think I have an explanation for that. He says, when the UV light did go in and hit the metal, the UV light had enough energy to knock the electrons loose off the ring. Kind of like, having a little bit of a loose tooth and you keep wiggling it with your tongue until it comes really loose and pops out. Yeah, the UV light was kind of doing that. It was wiggling those electrons loose. Because he says, think about the formula E equals HF. Your incoming light is basically determined by that formula because different frequencies have different energies. The frequency determines how much energy that quantum, that packet of energy has. So if EMR that has a lower frequency, like let's say radio waves, goes in and hits that metal, low frequency means low energy and it just doesn't have enough punch. to knock those electrons loose. But if we are talking about frequencies that are about UV or higher, so he considered that to be the minimum frequency, that it can be as low as about UV, which is higher frequencies, higher energies, E equals HF. It was just enough to knock off those electrons. He calls it threshold frequency because it's that bare minimum that we have to cross over, that we have to be at least as high as UV frequencies to have enough energy in the packet that hits that metal that it can start to knock the electrons loose. He gives it a special symbol. He writes it down as F naught. The little zero that you see there, we don't read it as F0, we read it as F naught. So it's not just a frequency, it's that minimum frequency we need, just enough that we can ensure that the energy that came in was able to knock loose those electrons. Now, it's fair to say, why is Einstein all excited that, hey, this is a particle characteristic again? Because frequency, we talk about frequency of waves, physics 20, we had velocity equals F lambda. Yeah, frequency, that's a wave thing. Well, consider this. I want you to imagine that you're at a beach and there's some really tiny waves coming splashing in. Maybe the waves are only about a meter, or not meter, I should say about a foot tall. Now those waves are just going to be banging against your shins basically. Are you worried about waves that are about a foot tall knocking you over? Nah. So that's where instead you've got to think about having waves that are really, really tall, like waves that might be 12 feet tall come crashing over you. That wave is going to be the wave that knocks you over. And that's because when we're talking about waves, amplitude, how tall the waves are, is how we measure the energy that they carry. Tall waves, big amplitude waves, carry lots of energy, so they're going to be the ones that knock you over. When I'm looking at this stuff here, am I talking about the amplitude of the UV? No. And that's how I would measure its energy if I was thinking of the UV as being a wave. But particle? Frequency? Okay, think of this. I've got one of those machines that can shoot tennis balls so that you can stand on a court and practice, hitting a tennis ball back without having to worry about anything to do with, playing against another person. Now, I tell you that you're going to stand on the other side of the court and I'm going to shoot a tennis ball at you once a minute. You can't move, you can't duck, and I'm going to aim it square in the middle of your torso. When that tennis ball hits you, I'm not saying it's going to be particularly comfortable, but if I have one tennis ball a minute hitting you, well, I'm pretty sure you're going to be able to take it and, for a few minutes at least stand there and get hit by a tennis ball each minute. But then I tell you, I'm going to turn up the frequency of the tennis balls. I'm going to do it so that now the balls are shot more frequently. There's going to be 60 tennis balls a minute. Every second, a tennis ball is going to be shot and hit you in the torso. Now, in this case, you're probably going to fall to the ground pretty quick and be asking me to stop. Each tennis ball is still the same mass traveling at the same velocity, but now they're more frequent. There's more tennis balls per second hitting you. So because there's more of them, each carrying their energy, they're hurting you. They're going to knock you down pretty quick. Frequency is a particle characteristic if we're talking about energy. So that's why here the frequency matters for the energy, and we can talk about it being a particle characteristic. Now, Einstein brings in another idea along with this, something called work function. And he basically says when a single electron is hit by a single photon, it transfers all of its energy to that electron. The photon ceases to exist. So it's got to pass over all of its energy that it's carrying. The whole packet, the whole quanta of energy has to go from the photon to the electron. That is going to be related then to the minimum energy needed just to snap off the electron to get it to break off of the metal surface, because we're always doing this shooting photons of light at metal surfaces. Because think about the periodic table, metals form positive ions because they're willing to lose some of their valence electrons. So Einstein called this the work function of the metal. He said it's the minimum energy needed, the work that needs to be done to snap off that electron from the metal surface. Every metal has its own work function. So that means we can actually distinguish them based on doing some sort of a measurement, which we'll get to soon, to figure out what metal it is we're dealing with, or maybe an alloy even, or something like that. Because this all starts to happen when we've met the minimum threshold frequency, F naught, we get a formula for it that we write down as W equals HF naught. So the W is this work function, the minimum energy needed just to snap off the electron. And it's related to F naught, the threshold frequency. Now, in case you're looking at this and saying, but hey, this is really just the formula E equals HF all over again, I hear you. But we switch to a different formula because we're now talking about something different. And we do that so that when we're doing big problems with lots of stuff going on, we can keep things separate. E equals HF, or you could write E equals HC over lambda. That refers to the energy carried by the photon that's coming in. So it's the energy of the EMR itself. It's what is being pointed at, the metal. It's what's going to interact with the metal. But W equals HF naught, we use that specifically when we're talking about snapping the electron off of the metal surface because it got hit by that photon. E equals HF, incoming photons of light of the incoming EMR energy. W equals HF naught, focusing on the snapping off of the electrons from the metal surface. So, what's the threshold frequency of a material, a metal, if its work function is 10 electron volts? I'm going to pull out the formula W equals HF naught, and because it's asking for the threshold frequency, I'm going to solve it for F naught. Work function is the 10 electron volts. It's the energy that's needed to snap off the electron. And since it's measured in electron volts, this is one of those I have a reason moments. I'm going to use Planck's constant in electron volts, 4.14 times 10 to the negative 15. And I find that that means it has a threshold frequency of 2.4 times 10 to the 15 hertz. Okay, great. So that means that if I shine light with at least that frequency or higher, then the electrons can be expected to be snapped off of the surface. At least the easiest electrons, the valence electrons, which would be the easiest to snap off. Now, what about if I switch things up a little bit? I say I want to know the work function of a metal measured in joules, so I'm going to use Planck's constant in joules. If the minimum, or sorry, I should say the maximum, I've got it written right there, if the maximum threshold wavelength is 1.10 times 10 to the negative 7. We got to think back even to like physics 20, V equals F lambda, or now that we're doing light, we can replace V with C for speed of light, C equals F lambda. We know that frequency and wavelengths are inverses of each other. So if when I'm talking about threshold frequencies, it's the minimum, it's the smallest number I can have and still snap them off, it means that the wavelength has to be a maximum threshold. This is the biggest that the wavelength can be and still be expected to snap them off. It also means that just like I have a formula that says E equals HF, which can also be shown as E equals hc over lambda, I can do the same thing with this formula because they have the same core construction, if you want to think of it that way. So work function equals hc over lambda naught. That's the maximum threshold wavelength. I am going to have to plug in some numbers now. I'm going to put in regular Planck's constant because apparently I want my answer in joules. I've got the speed of light, and I put in my threshold wavelength, which, by the way, if you look at it, if I move the decimal 2 places to the right, it'd be 110 times 10 to the negative 9 meters. That's 110 nanometers. 110 nanometers? Yeah, that's a little bit off to the side of the, where violet ends. So I'm in the ultraviolet here. I come up with 1.81 times 10 to the negative 18 joules. Now at this point, we talk about a fellow named Millikan and something he did called the photoelectric experiment. It's photoelectric because photo is light and electric, well, we're going to make some electricity actually with this. Now, one of the critical things to notice in this, because we're going to see this again and again now in a lot of the experiments from this point on, is this whole thing is happening inside a glass tube. Now, I know you can see there's a UV light source outside, and you say, but I thought you said glass blocks UV. Well, we can rig this up with some glass that doesn't block as much UV, and we can use a really strong UV light source, and yeah, everything will be okay. Don't worry about it. But the reason we put this whole experiment inside a glass tube, or at least most of it, is because we are doing quantum experiments now. That means that when you're dealing with things like photons of light and individual electrons, even just a little bit of dust floating around could be a pretty big thing to go smacking into. So we use a vacuum tube so we don't have to worry about any of that. The UV light source is shining down on a zinc plate. Okay, we'll get back to that later. But just so you know right now, it doesn't have to be a zinc plate. It could be a different metal. It's just, this is kind of the classic Millikan experiment. On the other side of the tube is another metal plate, and you can see it's connected by a wire that runs outside, connected to an ammeter that measures current, to the zinc plate. It goes back in on the other side, attached to the zinc plate. Now, what we have to think is, if this is like a circuit diagram from junior high, there's no voltage source, there's no battery, so that ammeter shouldn't show any current. And if you also want to look at it, there's the big giant gap inside the glass tube where it's not even a complete circuit. So there's no way we should be talking about, hey, look at all the electricity flowing. The ammeter should just be 0. But Millikan found that if he was shining the UV light on that zinc plate, the ammeter would show current. And that's because the UV light source has a frequency higher than the threshold frequency of the zinc plate. It's not just knocking off the electrons. There's also a little bit of leftover energy that's going to be kinetic energy, because work energy theorem, usually when we do work to something, it results in kinetic energy. That leftover energy is the electrons' kinetic energy shooting across the tube until they get to the metal plate. When the electrons get over there, the metal plate becomes negative, the zinc plate becomes positive because it's losing electrons, but those electrons aren't just going to sit on the metal plate, they're going to travel through the wire to get back to the zinc plate because they're repelled by negative, attracted to positive. Hey, if I've got electrons going through the ammeter, I've got a name for that. It's electrical current. So when he turned on the UV light source, he could get electricity to flow. Just so you know, this is, in a very primitive, basic way, how solar panels work. These people weren't trying to invent solar panels when they did this, but this is the way sometimes a discovery and the science we're doing and all that sort of stuff results in discoveries that have fortunate consequences for us. But he's not done there. He does something that seems a little bit weird. He puts in a variable DC voltage supply. And if you notice the way I've got this wired up, I've got the negative terminal going to the green metal plate, and the blue one going to the zinc plate. You might say, well, why is he doing this? Because that means even before he turns on the UV light, the green metal plate is already negative and the blue plate is already positive. Well, I want you to think of that as parallel plates. It means that he's got an electric field between those two parallel plates even before he turns on the light source. Now, when he turns on the light source, those electrons are, because there's still bajillions of electrons on the zinc plate, they're going to break off and try to fly to the left. But if they're trying to go away from a positive zinc plate and towards a negative metal plate on the other side, they're like trying to swim upstream against the electric field they're in. So what he reasoned is he could, if he adjusts that DC power supply until he gets just enough voltage, even the electrons that are traveling the very fastest to get across to the other side won't be able to make it. They'd almost make it to the green metal plate before they were thrown back and just go back to the zinc plate. It means that if he gets to just that point, the ammeter will show zero current again. He called this stopping voltage because to him, it's the minimum voltage needed, basically making an electric field between those two plates to prevent electrons from actually getting all the way across. That means even the fastest electrons that had so much of their energy after they were snapped off become the kinetic energy of flying across, they can't quite make it. That kinetic energy is taken away and they're tossed back where they came from. It's not a completed circuit and the ammeter just shows zero. I hope you can see that's why it's a good thing to call it stopping voltage. It's the voltage that stops the electrons from getting across. So how are we going to work this all into formulas and stuff? Well, let's look back at old formulas we've got. We've got a formula that relates voltage to energy. What I'm going to do is rearrange this. Delta E equals QV, and I'm going to rename some stuff. Delta E I'm going to call EK max, because those are the fastest moving electrons trying to make it all the way across, but not quite, because the V stop, stopping voltage, was enough to prevent them from getting there. Q is always the charge of an electron. And it's one thing that I know freaks people out in this chapter. Sometimes they'll come up to me after an exam and they'll say, I didn't know what charge to use, or I didn't know what mass to use. The only thing that we're throwing around when we do quantum mechanics by shooting like photons of light is electrons. So it's going to be the charge of an electron. If you're using mass, it's going to be the mass of an electron. But this formula lets us do some other calculations. Except what you're going to also find is that we don't necessarily just do a question where we just have you plug numbers straight into this. I could have a question like this, where I tell you that I know that even the maximum kinetic energy electrons that were being shot off that zinc surface were stopped when I made a uniform electric field of 16 newtons per coulomb between those metal plates that were 3 centimeters apart. Now you look at this and you say, this isn't quantum mechanics. This is like a few chapters back when we did electric fields between parallel plates. And I say, aha, you're right. Because we're getting to the point in physics where we can start drawing on so many different things that you've done in the past, both Physics 30 and Physics 20. So I'm going to look at this and I'm going to say, hey, I did stuff like this a few chapters ago, and the formula that works really nicely for this is E equals V over D. Electric field equals voltage over distance when I'm talking about parallel plates. So I'm going to solve this for voltage. Why? Because I can. Remember, sometimes we don't look at a problem and say, I'm going to get the final answer right now. We say, what can I calculate? And if I'm talking about electric fields between parallel plates, this is the formula I'm going to use. So let's get the voltage. I put in the electric field and I changed the 3 centimeters into meters by dividing by 100. And I get a voltage between those plates of 0.48 volts. And then I realize if I was able to stop the electrons using this setup, that voltage is the stopping voltage. And it was acting on electrons, and I know the charge of those, 1.60 times 10 to the negative 19 coulombs, so I can put it in, and I can find out that even the fastest moving electrons had a kinetic energy of 7.7 times 10 to the negative 20 joules. Now that's great. Actually, I prefer this answer because joules, especially for kinetic energy, means I can use the classic kinetic energy formula also. But I think it's worth pointing out to you that it's at times like this that I am sorely tempted to do that second calculation in electron volts. Because think, the charge is just going to be one elementary charge times the voltage 0.48. Done. I don't even have to hold a calculator. 0.48 electron volts. You can see why it's so tempting to do electron volts. We just have to understand that because it's not a standard unit, I wouldn't be able to use it with other calculations. Now this leads us to something I call the biggie formula. And that's not a formal physics term. It's just to me a good way of thinking about this formula because of all the parts it has. And it's actually got more than just what you're seeing there. So let's look at what this means to us. Remember, we start by shining a light on the surface. So I can use the formula E equals HF. I can take Planck's constant times the frequency to figure out how much energy is in the incoming EMR photon that's shooting down onto my metal surface. What happens when that photon hits the metal surface? Well, that's work function time, because the first bit of energy is going to be used just to snap the electron loose from that surface. And then any leftover energy, that becomes the maximum kinetic energy of shooting that electron so it goes flying off. Remember, work function is the idea that we're snapping off the easiest electrons. So that means we're leaving the most energy possible for kinetic energy flying away. Now, if you look at all three parts of this, and it's not necessarily immediately something that might jump out at you, the first part, the input energy, is energy. The work function is also energy. EK max is energy. So we're saying energy we start with becomes the energy we end with. That means this is really a statement of conservation of energy. And that can be a question we ask you. We talk about doing a photoelectric effect experiment and ejecting electrons from a metal surface and measuring stuff. And we say, so what physics principle is this? It's conservation of energy. Now, the way this becomes really the biggie, and the way that I think of it as being a big formula, is I wrote it down this way. But I have to consider that if I'm talking about the incoming energy, the part that I've written as HF, there's actually other ways I could talk about that. I could just give you the energy of the photon. I could also have you do a calculation with the wavelength of the light, hc over lambda, and that's all stuff about the incoming light. I could have you do work function based on just giving you the work function or telling you threshold frequency or threshold wavelength. And finally, EK max, yep, I could do it with QV stop. I could do it with classic 1/2 mv squared. I kind of think of this as a big giant slot machine, and I pull the handle, and I've got to use from each of those boxes the parts that fit the form or the question that I'm doing. So here's my example. I tell you that I know that the threshold frequency of silver is 1.14 times 10 to the 15 hertz. I'm shining some EMR on a piece of silver, and the wavelength of that EMR is 2.50 times 10 to the negative 7 meters. I want to know the speed of the electrons that are being emitted. So this is a classic photoelectric effect experiment question. Pause for a second, pause the video, and just make sure that you know what each of those pieces of information I've given you mean, and where they're going to fit, and what it is I'm asking you for. Okay, so I could start with the classic formula HF equals W plus EK max, which, by the way, is not on the data sheet because each of those pieces is on the data sheet. It's like when you're doing conservation of energy problems with a toboggan going down the hill. We don't show you EP plus EK equals EP plus EK, but you know that that's what you can use for conservation of energy. So we're building this, but we're going to change it for this situation because the EMR that's coming in, well, that's a wavelength. So on the left, I don't need HF, I need HC over lambda. Threshold frequency, I'm not going to use W, I'm going to use HF naught because that's threshold frequency. And I could replace EK max with 1/2 MV squared, but I am going to tell you I'm not going to do that. And my reason is if I do that and then I try to manipulate the formula for V, the velocity, whoa, it just looks ugly. I'm just going to leave it as EK max, and then I'm going to do that as a separate calculation. But I do need to manipulate this to solve for EK max. So I have HC over lambda, that's the incoming light, minus HF naught, the snapping off work function kind of stuff. And now I hope you can see why we had to use different symbols to show different things so we can keep track of it here. Now, before you say, hey, I'm going to cancel H because it's in both terms on the right, it's not on the left, so I can't cancel it. I do at this point usually have to make a choice. Am I going to do my question in joules or electron volts? Because that's going to be what determines what I use for Planck's constant. I'm going to say, because I want to find kinetic energy, I'm going to do this whole thing in joules. So that's my substitution. It's a lot. You want to be careful about how you're entering this into a calculator. You might want to do it in different chunks. I can understand why you'd want to do that, but you do have to go through all of this. The first chunk is all about the incoming light, and the second chunk is the work function stuff about breaking off the electrons. I go through all of this, and I get EK max 3.98 times 10 to the negative 20 joules. Now I'm showing it as a rounded off number there, but I'm going to use my unrounded number in the next step because I'm not done here. I want to know the speed of those electrons. So I grab classic kinetic energy. I solve it for velocity. I plug in all my numbers, and notice there's that mass of an electron because it's electrons that I'm doing this to. And I want to make sure that I also do a square root at the end. Otherwise, this number might turn out to be a little bit too big. But I go ahead and I do all that calculation, and I get a speed of 2.96 times 10 to the 5 meters per second, which perfectly reasonable speed for an electron. Now, what I would suggest is you spend some time with these questions, because what you're going to find is you got to be really careful when you're doing this stuff, because all of these terms and everything, it can be very easy to get turned around and misunderstand where you're putting the numbers and what you're being asked for. And the only way to get used to that is to do a bunch of questions. Good luck with that, and have a good day.